Dear conference organizers and participants, welcome to my presentation. My name is Baltic, PhD student at MCL in Austria. I'm delighted to participate in this conference to talk to you about our latest work, Calibration of Coupled Ductile Fracture Locus Model using Artificial Neural Networks. My talk is divided into 4 parts. I will start with the idea and motivation for searching an alternative method for calibration of complex damage models. Then we will look at our methods, that is finite element modeling and artificial neural networks combined together. Finally, I will present our first results on this topic and close with the main original contributions. We limit our attention to ductile fracture modeling. Based on the published literature and state-of-the-art models, it is fair to say that ductile fracture mechanisms are rather well understood and sophisticated stress state-dependent damage models have already been developed. Yet the complexity of the calibration procedure often hinders their application in industrial communities. Challenges we face frequently in determination of material constants are, for instance, too many parameters to be found or too less available experimental data. We are then forced to fit for one specific loading scenario, then large experimental efforts required, and so on. My objective today is to bring you closer to the computational framework developed for determination of material parameters by a machine learning method that integrates finite element modeling and artificial neural networks. In this work, we deal with parameter identification of coupled damage model that we published recently. The heart of the model is a fracture locus that quantifies the dependency of ductile fracture on states of stress and strain. Ductile fracture locus is defined by equation epsilon f, marked in red, dependent on stress axiality and load angle parameter. I think the graph perfectly shows how the model actually works. So when we are in high axiality regime, the damaged material will have a true stress-strain curve similar to the dark blue one. On the opposite side, when we are in low triaxiality regime, the material response will be more similar to the green curve. A non-local plastic strain is also introduced to regularize the strains in finite element model, and here the parameter L has to be adjusted for an adequate amount of regularization. So the model parameters to be found are fracture locus parameters, defining the equation epsilon f, and those are C1, C2, and C3. The C1 moderates the effect of the load angle parameter, and C2 represents the effect of stress triaxiality, which is expected to be dominant and more pronounced than effect of load angle parameter. So as this is our first work in this direction, we will fix C1 to one value and not vary it further in further computations, just to simplify the problem so that we stay with the 3 unknowns for artificial neural networks models. So we proceed with C2, C3 and L parameter as unknowns. The first step is to generate a training database, and for our numerical experiments we have chosen a shear specimen geometry. Here is the force displacement curve of real experiments, real tension experiments conducted on shear specimen. The parameter combinations in numerical experiments are designed according to Box-Benkin matrix of 3 variable system with 3 levels. So our 3 variables are our unknown parameters C2, C3 and L, and we have specified 3 levels, the minimum, medium and maximum one. This design was chosen because it seems to be very efficient. With only 13 models, we cover the whole design space. Here the graph shows a total of 13 simulated experiments. So all the force displacement curves resulting from simulations are plotted here. I would like to draw your attention to the values of the parameters varied. For instance, C2 is varied from 0.3 over 0.5 to 0.8. Or another example, C3 is varied between 2.2 and 2.8. And finally, the parameter L is varied from 160 to 210. Why I'm pointing this out? There are already published works on the applications of INN-based models to identification of damage parameters. However, to the best of my knowledge, the selected parameter range is frequently very restricted. That means the chosen parameter range is significantly smaller than this one. Here the goal is to find a robust parameter set from a broader range, because it is very likely that an engineer, when solving a real-world problem, does not have really an idea in which range the parameters lie actually. Once the training database is generated from finite element simulations, we are ready for passing the training data from finite element model to artificial neural network model. I would like to illustrate this point by showing you the following graphics. So the lower graph shows a force displacement curve of one of the numerical experiments. And then for every time t, we have extracted the displacement images in x and y directions, like these ones shown on upper pictures. And we have extracted force values through the complete numerical experiment. That means the two types of information are passed from finite element model to artificial neural network for learning. Those are local displacement images and the information from global force displacement curve. It's worth to highlight that in this way the local stress state evolution occurring in the tensile test is included in the model. The displacement images are extracted only from the zone of interest where the plastic strain develops. Turning our attention now to the INN model. Its architecture consists of 3D convolutional neural network, which is shown on left side, and 1D convolutional neural network shown on the right side. So 3D neural network involves the displacement images that contain x and y coordinates and the time t as the third dimension. And from 1D convolutional neural network, the so-called cuts of the force displacement curves are fed to the artificial neural network. After concatenation of those layers and after applying some regularization to avoid the overfitting of material parameters, the INN model should be then able to predict the parameters reproducing the real experiment, of course after the training. Before approaching the application of INN model to the real experiment, it is necessary to examine its quality. This is done by evaluating the model predictability of material parameters used in finite element simulations that are unseen in the training stage. That means that 4 additional finite element models are considered to examine the trained INN model quality. If you look at these graphs, an ideal case would be that all these points lie on the linear curve. That would mean that the prediction of INN matches 100% with the parameters used in finite element model. Once we are satisfied with the model quality, we can feed the data of a real experiment to the train INN. So the experimental data obtained from shear tensile test and digital image correlation analysis is introduced to the trained artificial neural network to identify the parameter set that predicts the real mechanical response of the shear specimen in terms of local strain distribution, the global force displacement curve, and the instant of fracture. The data is provided in exactly the same format as the training data. So we have the displacement images in X and Y direction and the cuts of the force displacement curve. Finally, we are coming to the results. So our current model predicts now the parameters listed in the table. The resulting global force displacement curve prediction is, so to say, satisfactory, as well as the displacement field images. However, the INN model is still to be improved to achieve more robust parameter predictions. So much for now. I would like to conclude by summing up my main points. So I have presented a computational framework for identification of material parameters, which is both calibrated and validated solely from numerical experiments. In the final stage of application, we have used the results of a real experiment to find the proper set of parameters. In the presented framework, we see a huge potential for further simplifications in determination of constants for complex material models. It is fair to say also that we are at the beginning of our work, and further work is meant to go in the direction of identification of all fracture locus parameters and including various specimen geometries. That brings me to the end of my presentation. Thank you for listening. I will gladly answer any of your questions.